Now let us look at a scenario like this. This is a very interesting scenario where we are talking about trying to apply a linear classifier. But think about this, is it possible to apply a linear classifier in a decent manner, even if we want to apply something like a multi-class SVM? I think the problem is, even if you try to do a vertical classifier multiple times across different angles, the problem is within the same region, again, you have a separator which is classifying in a different zone. But if you see, if you can apply something like a recursive partitioning, like the way we have shown here, it looks like that's a good way of dealing with this kind of a data. So this approach to handling this kind of a data, which is based on greedy recursive partitioning, is what is known as decision trees, and is also able to tackle one more important thing, which is about rule-based systems. We say that when we talk about handling large information systems, typically they are governed by certain rules. So our task is to identify what are those rules which are describing this behavior. Sometimes these rules may be driven by business logic, sometimes they may be described by something which is explaining the way the system works, or sometimes these may be government rules which decide on how your systems behave. But the idea is, a lot of times we are working with rule-based systems in your knowledge bases. That's exactly where this greedy recursive partitioning and rule-based approaches converge. And that is what we call them as decision trees. Decision tree is an approach where you try to identify at the top level one influencing variable, input variable or a feature, try to divide the data into different possible outcomes. Then for each path, again you look at another variable, again you divide into further possible values of that variable, and so on. So decision tree, the way of looking at it is you can view it as a collection of rules. If you take one path from top to bottom, so let's say outlook equal to sunny and humidity equal to high. Similarly, you can have outlook is overcast. Similarly, you can have outlook is rainy and wind is weak. So there are several rules that can be generated, and typically what happens is when you are given a new data, you go across one of these paths, and then that is the rule which satisfies your particular input condition. So if you see the example, let us say we have something like a sunny and it is say humid. Then we will say that the resulting class should be no, in the sense the possibility of the rain is no. Similarly, you can traverse different paths depending on your input conditions, see which rule applies, and you can decide upon the right output class. So what happens in this is basically we try to go across the whole sample and try to identify how you can build a tree top down based on the notion of information gain. This is a concept from information theory, which is basically based on the notion of entropy. And that makes us decide upon what is a variable which you should start branching from. Then at each branch point, then what is the next variable you're going to branch out. So that is basically done using the notion of information gain, or how you can create a better entropy. In the sense, if you take a perfectly homogeneous sample, entropy will be zero where there is no classes, all of them are one class. If all of them are equally divided in all classes, entropy is one. But the usual reality is it's somewhere in the middle between 0 and 1. So we try to look at deriving the entropy, and based on that, we try to see how you can increase the entropy of the system. That we will select that kind of a classifier. Again, just like linear classifier, you had a scenario where you had several possible lines separating the samples. Even in decision trees, you get the same. You have potentially several variants which could explain. But then you have to stop somewhere where you have a reasonable idea of, okay, here is where I'm happy with the entropy gain. Here is a reasonable error which I can live with. And that is where we say that in order for us to be able to get a better decision tree, a lot of times we may have to do backtracking. In the sense, we create first a pass of a tree, but then it is possible that there may be, some paths which we have not explored in this probably greedy algorithm, and then we backtrack and merge children nodes and then go back, try and find alternative paths, then stop at somewhere where your defined uh, you know criteria for entropy and information gain is reasonable. So don't think of this as a one shot, one exploration from top to bottom and you create a decision tree. Of course, initial algorithm ID3 was doing like that. It does not use backtracking. But later algorithms have been using variants of this to create backtracking. Once you even reach a leaf node, you try to even merge backwards, upwards, go and explore alternative paths. Example entropy calculation is given here. Suppose you had two uh, elements, x and y, and the entropy of the system would be based on how something would be p equal to 9 out of 14, q equal to 5 out of 14. Based on that, we will create this formula of sigma of pi log p is the entropy of the system. The problem with